Okay, we get to talk about a very fun method for finding antiderivatives, a very special class of functions. And this method is the method of partial fraction decomposition. Some of you may have actually performed the actual partial fraction decomposition in a pre-calculus course. And to illustrate this method, first of all, before we use it, I want to sort of go opposite the direction we'll be going, actually, and I'm going to add the following rational expression. This should be singular here, sorry, expression. I want to add, well, I guess S actually is true. I've got two expressions. Okay, I'm going to add these two together. So remember how we add together, we need a least common denominator. And what's the least common denominator for these two rational expressions? Since the denominator for both is prime, just a binomial prime factor, the least common denominator is the product of those two. And so it's x minus 1 times x plus 3. So I'm going to get a common denominator so I can add these. This one, of course, I'm going to multiply by what? X plus 3 over x plus 3. Multiplying by 1. I'm not changing the value of the expression, but I am going to get it over that common denominator. And the second rational expression, I'm going to multiply by this quantity, which again is 1. And so when I do this, I now have both of them over the same denominator, which is x minus 1 times x plus 3. And the numerator, though, I can add, right? This will be 4 times the quantity x plus 3 plus 2 times the quantity x minus 1. I think my pen is running out of ink. I'm going to change. So now I can do some simplification here. I can distribute the 4 and the 2, and I get 4x plus 12 plus 2x minus 2. And then combining like terms up top, 4x plus 2x is 6x, 12 minus 2 is 10. And there I get the sum now. So I've written the two rational expressions as one rational expression. Okay, and so of course I can possibly simplify this further. Up top I can factor out a 2, leaving 3x plus 5, but there's no common factor in the numerator and denominator in this case, but I could simplify if I wanted to. But the important thing is I'm not concerned about that. I'm just concerned with the process. I hope everyone understands how to go from here to here. You should. This is something you learn in algebra and intermediate level algebra, being able to add rational or fractional expressions, right? Okay, so what we're going to be doing with the partial fraction decomposition is taking this fraction, this rational expression, and breaking up into its parts, if you will, breaking it back up into this sum. So I want to start with this and get back to this. That's the goal. Okay, so that's a pre-calculus topic, really. And what that's going to allow us to do, though, is to be able to integrate functions that look like this by rewriting them this way, and then these functions are easier to integrate. Okay, so that's what the method of partial fraction decomposition is useful for us. So we're going to use this to integrate functions of this form, n divided by d, where n and d are polynomial functions. So it's a special class of functions we're focusing on in this integration technique. Okay, so here's the nuts and bolts, and then we'll look at it specifically, but here are the steps to put the rational function f of x into its partial fraction decomposition. By the way, I will sometimes abbreviate partial fraction decomposition as PFD. So if you ever see PFD, that stands for partial fraction decomposition. Okay, one thing is that the numerator degree must be less than the denominator degree. All right, numerator must be less than the denominator. If you go back to that previous example, the top here has degree 1. The bottom, if I expand this out, is x squared degree 2. So that's in the right form. If it's not the case, if the degree of n is equal to or greater than the denominator, we're going to have to do some division, some polynomial long division, synthetic division if it's applicable. You remember how to do that, so I'll review how to do that. When you do that, you'll get a polynomial plus the remainder, right, over the divisor, and then this will be something that we could potentially, if we have to, do the partial fraction decomposition on. Okay, so that's the first thing. If indeed the numerator degree is less than the denominator degree, then we can do the partial fraction decomposition as follows. We factor the denominator into factors. The factors are either linear factors. So how do we know a linear factor? Here the p, q, and m are going to be real numbers. The m is an integer, a positive integer, or zero, so a whole number, I guess we should say. But the linear factors, right, are pq plus px plus q. Right? In other words, it is just x is the highest degree term, first degree terms. Okay, so linear factors or quadratic factors, where these factors here, ax squared plus bx plus c, is a degree 2, right, factor. Quadratic is degree 2, but it's prime. In other words, it can't be factored into linear factors, so I couldn't factor it. So prime are what we call irreducible over the rationals. We won't look at any problems where there's cubic prime factors in it, and so we won't go in that direction. We will go up only to quadratic factors. Okay, so for each linear factor of the form px plus q, I keep saying that, px plus q to the m power, the partial fraction decomposition must include the following sum of m fractions. So notice the number of fractions is associated with that exponent. So whatever that exponent is, if it's 1, if there's just one linear factor, there's just going to be one fraction in contribution to our partial fraction decomposition. If it's squared, the linear factor is being squared, then there'll be 2. If it's cubed, there'll be 3, and so on. And so we keep going on, and each one will have the linear factor to the first power, to the second power, to the third power, and so on, depending on what m is, right, all the way up to m. And up top, I've got this a sub 1, a sub 2 to a sub n. Those capital A's, they're going to be real numbers. Those are the numbers we need to find. If I go back to the example, that's like the 4 here, or the 2. When we break this up, notice there is one linear factor down here, x minus 1, and there's one fraction from that. There's one linear factor here, x plus 3, and there's one fraction from that. Okay. Now, it is true if I have m, if this is to the m power, let's say it's 4. Let's just put if there's 4 here. So I have 4 fractions. I may have less than 4 fractions because some of these constants, a1, a2, up to a4 in that instance, some of those could be potentially 0. They could be 0, which would sort of wipe out that fraction. So you have up to that many. For each quadratic factor, right, again, look at the power n, right, of that. We will have that number of fractions or less. And notice the difference there is for each one, the numerator is not just a real number like a, but it's a linear function, b1x plus c1. So we have sort of b1 and c1 are the things we have to find. So I can have like 2x plus 1 over some, x squared plus 1, some irreducible or prime quadratic factor. Okay, so this is the nuts and bolts, and of course finding the values of a1, a2, and b1, c1, b2, c2, and all those, that's an algebraic problem that we'll look at how to solve. And then once we've done all that, then we'll do the calculus. So this is all pre-calculus stuff. Let's make sure we understand how to write out the form then, first of all, before we actually find those values. So this is just writing out the form, not finding the values of those constants. Now, I used A1, A2, A3 in these examples, capital letters A1, A2, or B1, C1, B2, C2, and so on. I'm just going to use capital letters, but I'm just going to go A, B, C, D, E, and so on, just how many unknowns I need. That's the way I'm going to do it in these examples here. So the first thing is, notice the degree of the top is 1, the degree of the bottom is 2, so it's in the form we need it to be in. I'm going to factor the denominator. That's the first step. Numerator is unfactored. Don't worry about that right now. How does this factor? Product of the two numbers is 3. They sum to 4. Obviously, it's plus 3 and plus 1, right? So I have two linear factors. X plus 3 is linear. X plus 1 is linear. That means for each one I will have, whoops, what am I doing here? Equals. We will have one fraction. So for this x plus 3, I'll have some constant, some real number over x plus 3. Because it's a linear factor, I just have a constant up top. Plus what? Some x plus 1 b, right? And so, this is, just the opposite of what we were doing a minute ago, right? When we were taking this expression where I knew a and b and adding them together to get this. Now we're breaking this up into this. So what is a and b? And we'll talk about that here in a minute. How do we find a and b? Right now I just want to make sure you get the form correctly. Okay, this is the form of the partial. Now a and b can be any real numbers. Okay. Now look at this next example. It's factored for us. The denominator is already factored. Notice it's degree 2. If I were to FOIL this out, expand this out, I get x squared plus 10x plus 25, right? Degree 2, top is degree 1, so it's in the set form we need it to be. The denominator is factored. But this time, there's only one. This is a linear factor, but it's to the second power. So remember what that means. If it's the second power, we'll have two fractions. The first one will just be x plus 5 in the denominator, and again some real number a, I don't know what it is. The second one will be x plus 5, that linear factor, squared, right? Again with some constant we don't know. So again, as long as it's a linear factor, right, if there's just one, x plus 3 to the first, there's just one fraction for that. X plus 5 to the second, 2, there's two fractions for that. And you see how the denominators change as we go through. Again, finding a and b, we'll talk about that after a while. Now look at this one. This is degree 3 up top. If I FOIL this out, x squared times x squared, x to the 4th, right? I'll have a 4th degree polynomial down here. So degree of top 3 to degree of the bottom 4. So it's in the correct form, degree of the top less than the bottom. And I factored the denominator. This time, notice x squared plus 1 is a quadratic factor, and it is prime. You cannot factor x squared plus 1 any further. Right? It's not x squared minus 1, which we could factor further, right? Difference of squares. Sum of squares is prime over the rational number, so I can't factor that over rational numbers. And again, that's the key. We don't want to factor over irrationals or non-real numbers or anything like that. Okay. So what does this mean now? So remember what we said, when we have a quadratic factor, it's a little different. The partial fraction decomposition will involve a linear factor over that quadratic. And again, since if there's a power here, that's how many fractions we should address. So there is a 2 here, so we're going to have two fractions. The first one, we'll just have x squared plus 1, that quadratic factor. But up top, notice I have a linear factor. Okay, degree 2 up in the bottom means degree 1 up top. Degree 1 on the bottom here means what? Degree 0. If you're just a constant term, degree 0. So you see how that's working. The next one we will have what? X squared plus 1 squared. Now, of course, this is degree 4 if we expand it out. But again, it's this quadratic factor, right? And again, it's going to be linear up top. So I'm going to use a and b. Now I need what? C. X plus d. I'm just, different unknowns. So I've got to find the values of a, b, c, and d. We're not going to do that for this problem. We'll show you how to do that here in a minute. But again, those can be any real numbers. Okay, that's what we need to do. Let's do this last one. This one is degree 2 up top. The bottom is clearly what? 1. This will be a cubic. This will be degree 4, degree 4. Degree 3, degree 1. If I add those degrees up, the highest degree term will be degree 8. Okay, but the bottom line is top degree greater than top degree less than degree of the bottom. So it's in the form it needs to be. But this time, look, I have 1, 2, 3 sort of sets of factors. Now this x factor you can think of is linear. Think of it as x plus 0 or x minus 0. We usually don't write x plus 0, we just write as x. So it's actually a linear factor. And so it has one fraction because there's just x to the first power. And since it's linear, I just have a constant up top. The second factor is x plus 7, and it's to the third power. That means there's 3 fractions for that. There's x plus 7. It needs a constant, something else, b. X plus 7 squared, and x plus 7 cubed. Okay, so we got 3 from just that one. And then the last factor here is quadratic. X squared plus 4 is prime, can't be further factored, so that's degree 2. And it's squared, right? So there's 2 of them. So I've got 1 x squared plus 4. That's a quadratic right now, so we need what? I left off with d, so I'll do ex plus f. And then the last one, x squared plus 4 squared, fgx plus h. Ooh, okay, so that now a, b, c, d, e, f, g, h, those are real numbers, and so your task is to find those real numbers. How do we do that? We're going to talk about that next. Again, some of these numbers could be 0, which, you know, if b was 0, that means we wouldn't actually have that fraction in the decomposition, and that's okay. But you could. I mean, these could all be non-zero. And so this is the idea behind the form of the partial fraction decomposition. So let's show you how this works, and we'll also show you how it involves you know, finding the antiderivative. Okay, antiderivative. Let's go back to this one here. How do I find the values of a and b here? Let's take a look at this one. So here's our first example now of the method. So you can, this is that same one we had, so 3x plus 13. Remember, the denominator factors is x plus 1 times x plus 3. And we said the partial fraction decomposition looks like this. Okay, so one way how am I going to solve for a rational equation? Do you remember how you solve for a rational equation? Now be careful, I'm not going to be solving for x, but we want to find the values of a and b. But I am going to still use that same technique, which is to multiply both sides of the equation by the least common denominator of all your fractions. And clearly that's going to be this factored denominator over here on the left, which is x plus 1 times x plus 3. Okay. When I multiply both sides by that, what happens when I multiply this by x plus 1 times x plus 3? Well, I'm just left with 3x plus 13, right? Because the x plus 1s and x plus 3s, you know, cancel, right? And then here, a over x plus 1 times this, the x plus 1 will cancel, and I'm left with x plus 3. And here, when I multiply, the x plus 3's cancel, and I'm left with x plus 1. Now, so this equation has to be true for all values of x. Okay. Now, obviously, we know from the first equation, x can obviously not be what? -1 and -3 in this equation. But it can be down here. Okay. And the thing is, this equation is going to be true for all real numbers. All right. And so a and b have to satisfy this equation for all real numbers, including -1 and -3. Up here, it's going to satisfy for all real numbers. A and b will be the same for all real numbers, except for what? -1 and -3. However, the a and b here will be the same as the a and b here, and we can use all real numbers here, but we can use only all real numbers except for -1 and -3. Okay, so the bottom line is I'm going to show you a shortcut for finding a and b, and that is actually now with this equation, the shortcut is to actually plug in those values of x that were restricted up here but not restricted here, because something magical will happen. So if x is -1, which we could not use up here, but which we can here in this equation, what do we get if x is -1? Just replace x with -1. I get 3 times -1 plus 13 on this side. Here I get -1 plus 3, and plus what? B times -1 plus 1. Obviously, this whole thing goes to 0, right? -1 plus 1 is 0. Whatever b is, you know, it's going to be 0. Okay, but what do we have left? -3 plus 13 is 10, and what's this? -1 plus 3 is 2 times a, 2a. Look at this equation now. Do we know what a is now? What must a be here? Obviously 5, right? We've found a value. And here's the thing. This value of a here has to be the same as up here. Okay? Again, I can find it here because I can let x be -1 here. Up here, I can't let x be -1, but this value of a is the same for all real numbers x. Okay? So it has to be true for -1. And this a is the same as that a. So it's a really cute, cool little shortcut. So what's the other value of x I'm going to use, right? -3. And notice when I plug in -3, I get 3 times -3 plus 13 equals, okay, that's going to go to 0, right? A times 0, because if I plug in -3, I get 0. And then what do I get here? Plus b -3 plus 1, which is -2. So I get -9 plus 13 is 4, and this is -2b. Divide both sides by -2, and I get b is -2. And I found my two values. So now I know the partial fraction decomposition. The way to break this up is what? 5 divided by x plus 1 plus a -2 over x plus 3, or -2 over x plus 3, right? And that's the way I'm going to write it. So I'm now going to come back and take this and write this as the integral of a, which is 5 over x plus 1, and then what, plus b, which is -2, plus a negative, or -2. I'll just write that as -2 over x plus 3. Now, the very first problem we did in this video, we looked at a problem like this where we combined these two fractions. We were adding here, we're subtracting. You should be able to do that. Go ahead and do the subtraction as a check. I would encourage you to do that. Make sure you go ahead and check this. Indeed, if you subtract, find a common denominator, subtract, and simplify, you get right back to this. You get right back to what we started with. They're the same. That's the whole point. But now, in this original one, we couldn't find the antiderivative. Some of you might have said, hey, I can let u be, do a simple substitution. U be what? X squared plus 4x plus 3. But what would the du be? It would be 2x plus 4. If I take the derivative of the bottom, 2x plus 4. Well, 2x plus 4, this is not a multiple of 2x plus 4. If this was 2x plus 4 up here, or a multiple of it, this would just be a simple du over u, 1 over u integral, which would evaluate as the natural log of u. But that's not the case here. But when I split it up, now I can do each one, right? Notice each one is a 1 over u integral. Like this one, if I let u be x plus 1, then du is just equal to dx, and this becomes the integral of, this 5 comes out, right? Du over u, which is 5 times what? The natural log absolute value of u plus a constant, right? That's that. And this one's going to be what? -2 over the natural log of u, where u is x plus 3. So this is very simple substitution. In other words, this then becomes what? 5 times the natural log absolute value of u, which is what? X plus 1, minus 2 natural log absolute value of x plus 3, plus our c. There's the antiderivative. There's the antiderivative. Okay, and that's the way I would have you write it. Now, properties of logarithms, you can bring these exponents up, log of x plus 1 to the 5th minus log of x plus 3 squared, in other words, and then you can say the difference of logs is the log of the quotient. So all this could be written as the natural log of the absolute value of x plus 1 to the 5th over the absolute value of x plus 3 squared. Okay, so that's a nice form. I'm fine with this. I don't want you to have to do that. If you're checking your answers in a book, or doing it, doing a problem online or something, they might use a form like this. And sometimes it's nice, it's more compact, and you can simplify what's in here possibly, and simplify your answer, which is fine. But just getting this point, I'm happy right now. Okay, so that's our first little one. We've got several more to do in the next videos, and so we'll pause here. In the next videos, we'll do more examples. This is a simple example. We're going to do some more examples, some examples where we have to do polynomial long division, and so you'll need to review that, and we'll look at that next.